We'll be speaking for the next hour or so about protein folding. We're going to begin with a discussion of what protein folding is in vitro and how we might study protein folding and what we might learn from studying protein folding. And then we're going to move on to some issues in vivo protein folding and in vivo protein stability. First of all, just a reminder, what I stated at the beginning of the semester was that all the information required for a protein to adopt its three-dimensional, native, functional organization is the sequence. And that's true for many, many proteins. And so what I've drawn here is a very simple little DNA binding protein. Doesn't matter what it is, but above there is its primary sequence right there. And here's the fold. Somehow this molecule in isolation, a pure protein, can be folded and unfolded and refolded indefinitely, right? So this is the only thing that's happening, is moving from the folded to the unfolded state, or the native to the denatured state. How does it do this? It's one thing to make that simple statement that proteins can fold simply based on their sequence information. It's another thing to understand the mechanism of how that takes place. So let's move to the next slide. And here I've taken some words and a table out of this very early paper. I'll remind you that Chris Anfinsen won a Nobel Prize for his work in characterizing protein folding and establishing that fact that proteins can fold and unfold without assistance. Let's just read. The 4 disulfide bonds of bovine pancreatic ribonuclease can be reduced with mild reducing agents to yield a product which contains 8 sulfhydryl groups and appears to be free of other covalent change. By exposing a dilute solution of the reduced polypeptide chain to molecular oxygen at approximately neutral pH, the reduced derivative is converted to the original native form in essentially quantitative yields. So what's he talking about here? This protein, ribonuclease from cow pancreas, has a bunch of disulfides. 8 sulfhydryls, so how many disulfides? Well, let's assume 4. Those can be reduced by the addition of something called a reducing agent. I'll show you what that means in a minute. But basically, we're breaking the disulfide bonds that hold that molecule together. Exposing the solution to oxygen allows those disulfides to reoxidize, right? So when we reduce it, we lose the activity of the ribonuclease, and then we regain the activity when we just expose the solution to air again. And in terms of the table, let's just look at the bottom here, right? This is various concentrations of protein, but bottom line is that we can regain the activity after reoxidation of the disulfide bonds. And this was the big result, right? Protein can lose its activity and regain it simply by allowing the thing to refold. Nobel Prize. It's a different world today. This is bovine pancreatic ribonuclease, the structure of that molecule, stolen off of Wikipedia. What I'm highlighting here is 1, 2, 3, 4 disulfide bonds. And note the sequence relationships here, right? These are not necessarily very close in sequence, right? Here's one that's 65 to 72. That's not very far in sequence. But 40 to 95, 26 to 84, those are very sequence distant sulfhydryls that have now tied the protein together. In purple here we see active site residues, not relevant for us. So here's a disulfide bond. We can add a reducing agent such as mercaptoethanol, beta mercaptoethanol, and what happens is, right, reduction of those disulfides, and in favor of the oxidation of the mercaptoethanol itself. So that's how we'll lose that stabilizing interaction and lose our activity, easily regained when we remove the reducing agent. So proteins can fold. Okay. Well, what does that do for us? So before I talk about protein folding per se, let me talk about stability. So we can imagine that there's some intrinsic stability to this molecule that depends on the presence of those stabilizing disulfide bonds. what is the stability? So that's how easily how easily the protein loses its structure. So we'll present that as a quantity, an energy, because of course as chemists we like to be able to put a number on that value, and we'll see some good examples of that in a moment. But how do we measure the stability of a protein fold? How do we measure protein folding? Well, spectroscopy is the answer. There are other methods that aren't spectroscopic that we can use, but the simplest means of monitoring protein folding are by using the interaction of the protein with various kinds of radiation. The key here is that there's got to be some change, right? Not only between the folded and unfolded states and the populations of those two states, but that also has to result in some uh, change in the spectral characteristics of the molecule as well. So when the protein changes conformation, so too must the way that it interacts with light change. There are a few different ways that you can monitor protein folding. Circular dichroism is one, which I'll explain in a moment. Probably most familiar to you is the idea of fluorescence. We've talked about it in class. You can use the fluorescence of intrinsic chromophores or intrinsic fluorophores such as tryptophan, or extrinsic chromophores. That is, you can label the molecule with a dye of your choice to fluoresce at a particular wavelength. Nuclear magnetic resonance is another one, and we've talked about this one in class as well. In any of these cases, what we're talking about is a change, for example, in the fluorescent spectrum of the protein between the folded and unfolded states. So that's your spectroscopic handle on the folding event or the changing in populations. The idea here is that some structural feature that we lose upon denaturation has an impact on the spectral characteristics of the protein. So unfolding means that we lose our structure-related optical activity. That's circular dichroism. I'll explain that again in a moment. We change the exposure state of some buried tryptophan. Remember, tryptophan's hydrophobic amino acid side chain typically going to be mostly buried in a protein. You could imagine that its spectral characteristics will change depending on whether the molecule, the amino acid side chain, is buried or exposed. Likewise, in terms of NMR, unfolding is going to change the local chemical environments of the protein. That's going to change the chemical shifts of a particular spin, a particular nucleus. We'll come back to that idea in a moment. So, but remember that we have a lot of ways of monitoring protein folding by looking simply at the spectroscopic characteristics of the molecule, and all of those depend on the protein. All of those methods depend on some change taking place. So proteins unfold. I wanted to show you again a little 1973 article from Amundsen. This is his Nobel acceptance speech. This is a protein unfolding curve that as a chemist we would like to quantify and use as a model. So what are we looking at? Well, we see here the percent of some total change, so that's just a fraction of whatever change we're observing, here as a function of pH. So we can unfold this molecule, we can force it to go through some conformational change by stressing the system in some way. That can be via pH, that can be by solutes, that can be by temperature. What do I mean by solutes? Well, the typical molecules for unfolding proteins are urea and guanidine hydrochloride. Structures of those we don't necessarily care about, but for now you can just remember that these are the two important denaturant chemicals that are used in biophysical characterization of proteins. Here what we're looking at though is pH, right? So we've changed the pH and we undergo a structural change. The boxes are reduced viscosity, so we're measuring the viscosity of the solution as a function of pH and seeing that it depends on the folded state of the protein. And in triangles here we're looking at the molar ellipticity of the protein. So that's the circular dichroism effect, and that I'm going to describe again in a moment. But whichever the effect, whether we're talking about some this is never used anymore, but some visco elastic effect versus a circular dichroism spectroscopy, we see the same behavior, right? That is to say, the protein unfolds at pH 4. If you were looking at this, you'd say, well, what does that mean? What happens above pH 4 that would cause the molecule to begin to unfold? Well, I don't know exactly, but I'd like you to think about what could be happening as we move through pH 4 that you might imagine would cause the protein to unfold. We'll talk about that in class. So think about it. So let's look again at these metrics of protein folding. So on the left here, we're looking at circular dichroism spectra. Right, here's wavelength, and this happens to be a complicated metric of circular dichroism. I'll describe it in a minute. Basically, it's the degree of rotation of the radiation. Let's think about this. Optically active molecules differentially absorb left and right hand circularly polarized light. It results in an ellipticity. So this theta here is effectively an ellipticity, or the number of millidegrees of rotation that for each particular wavelength. The key here is that, okay, optically active, you're used to thinking of in terms of chirality, probably for optical activity, but in fact, structured proteins are also optically active. By virtue of their folded structure, that is a kind of chirality, if you will, although not in the formal sense. But it does result in a strong circular dichroism spectrum. So what's a circular dichroism spectrum? So we interrogate our sample with right hand and left hand circularly polarized radiation, and we see that optically active structures have a differential absorbance of the left and the right. What that results in is, when you recombine those two components, is an elliptically polarized radiation, right? If it's not perfectly absorbing the left and the right, then you see an ellipticity. That's what's measured here, and it's a small effect, right? Thousandths of a degree, right? But still quite noticeable. And the key for us is that different secondary structural classes have very unique signatures in circular dichroism. Even more important, though, is that when we monitor these signatures, whether we're in a helix or a beta strand, as a function, say, of temperature or denaturant or pH, then we see that if we look at, say, the black to the green line, right, if we monitor at 220, which you remember in the last slide Anfinsen was doing, you see a big change when you denature that protein. So there's your spectroscopic handle in terms of circular dichroism, and this is a very commonly used method. Why? Because all folded proteins are going to have a circular dichroism spectrum that's going to be obliterated when we unfold it. So you're not depending on, for example, the presence of a fluorophore like tryptophan in your molecule. Let's look at fluorescence, though. In this little spectrum, we see clearly, well, there's tryptophan. Remember, it has a strong absorbance in the ultraviolet, and it also fluoresces, slightly redshifted up, or longer wavelength emission from its absorbance. And if we look at the folded spectrum, this is the emission spectrum, right? If we excite this guy by exposing it to radiation at, say, 280 nanometers, that's the peak of its absorbance, by the way, and we monitor where it emits light, right, then we see that over this wavelength range, 300 to 400 nanometers, we have a peak in absorbance at 340, but that we lose that, in this case, for whatever this protein is, doesn't really matter, that we lose that fluorescence when we expose the tryptophan to water, right? So there's a big spectroscopic change. Not only is there a loss of intensity, but there's a shift to the red of the fluorescence maximum. So tryptophan emission depends on the environment. In this case, the folded state of the protein supports a stronger fluorescence, and then exposure to water when we unfold the protein results in the quenching of fluorescence. But it doesn't have to be this way. There are plenty of examples in which a fluorophore, a tryptophan, is butted up against a sulfur atom or something like that in the folded state, buried in the core, but up against a methionine, for example. That will quench the fluorescence in the folded state, and we'll actually see an increase in the unfolded state. But the bottom line is that there's a change that we can observe. Oh, while I'm on the story of chromophores and fluorescence, I'm just going to mention green fluorescent protein. Why am I showing you this picture? Well, okay, let's draw our attention to the last one. Suffice it to say, however, that GFP, green fluorescent protein, can be the spectral characteristics of the molecule can be radically altered simply by point mutations and other kinds of changes in the sequence of the protein. And we can see that we can have a blue fluorescent protein, or a cyan fluorescent protein, a green fluorescent protein, just by changing the composition of the chromophore. So here we've got a histidine in this position, here we've got a tyrosine in this position, here we've got a tryptophan. So we see that we're jumping all over the place in terms of the fluorescence emission of the molecule. But here I've highlighted in the bottom right a yellow fluorescent protein. Why am I showing this to you? Again, because in this case there's a tyrosine 203 that stacks on top of tyrosine 66 that very dramatically alters the fluorescence of the protein, shifting the fluorescence emission far to the red, and now we have a yellow fluorescent protein. So the environment, the point is, the environment of the protein affects the fluorescence characteristics of the molecule. When we disrupt that environment by unfolding it, we again change those characteristics and see a change. NMR, same idea, except now what we're talking about is remember the radio frequency at which a particular nucleus resonates, right? And each nucleus, each atom in the molecule will have a particular resonance chemical shift, right? And that is going to depend on all of those unique environments that are present in the folded state. We lose those unique environments when we unfold the molecule. Effectively, all the nuclei are exposed to the same chemical environment, and we get a much more simple two-dimensional NMR spectrum. So I remind you that what we're looking at here is a 2D NMR spectrum, protons on the x-axis, nitrogen frequencies on the y-axis. So again, fingerprint of all of the nitrogen proton pairs in this particular molecule, FIN-SH3. We don't really care what that is. It does. Some of you may remember that I've said SH3 domains are protein-protein interaction domains. The FIN-SH3 domain is simply a kind of a standard model system for studying protein folding. These are spectra that I collected, oh gosh, starting to get to be a long time ago. That's why I haven't referenced myself here. In any case, we see that we have a well-dispersed spectrum. All of these individual nitrogen proton pairs have their own environments, their own chemical shift sets. When we expose this molecule to a high concentration of guanidine hydrochloride, remember that's that denaturant, then we lose all of that interesting spectral features in the NMR spectrum, and clearly this molecule is unfolded. It is interesting to note, though, that all of the proton frequencies are more or less the same, 8.5 or so, but we're still distributed across nitrogen frequencies. Something that you see that doesn't change in this case, these are the amino protons, right? It's not peptide, not backbone amide protons, but these are side chain protons here. Anyway, these chaotropic salts, right? They disrupt the structure of water, guanidine hydrochloride, disrupting the structure of water, forcing the molecule to unfold, and we have our spectroscopic signal. So coming back